All right, let's get started. In last chapter, we talked about the basics of Monte Carlo integration, where we have these kind of estimators that can work on high-dimensional situations like in rendering, but sometimes the variance of those estimations can get very large, and a lot of times we don't have that much time to generate so many samples, so we want to reduce variance, and that's what's the topic today. So the first technique to reduce variance is so-called stratified sampling. So stratified sampling decomposes the integration domain into regions and then place samples in each one. So stratified sampling subdivide the integral domain. What's this thing again? I don't know how to pronounce that. But anyway,
Isn't that just lambda, but the capital form of it?
okay, we will just call it lambda then.
Yeah.
So yeah, we subdivide lambda into like lambda 1, lambda 2, etc. Call them stratum. I never say this word before, but yeah, each stratum is just like all the stratum combined is the original domain, and then we draw samples from each one. And then this is the full analysis that this indeed reduce variance. But to be honest, I got confused about this part.
So is this just saying, okay, we have many subsections of our total sampling area, and we want to make sure to sample the areas that are most important to our contribution, or most contribute the most, or
No. That's
because
we're not talking about importance sampling
right,
yet.
right, that
This
makes more
is
sense.
just, for example, we do some kind of super sampling and then subdivide the pixel by a grid, for example.
Uh,
So I guess this is more about just trying to guarantee that the samples you take cover the whole range, right? Rather than being clumped in some region by accident.
Just because like random uniform sampling can result in clutter, and with this we guaranteed like samples are like kind of better distributed.
mm,
I guess we will just not talk about this analysis. Kind of really dense stuff. I think I got lost at here, basically. The result is quite nice.
yeah, minimizing the randomness of white noise is a good thing because it is very random and therefore full of possibly missed things.
Yeah. I wonder if something like Poisson disk sampling can achieve the same effect, like blue noise, because really a downside of this stratified sampling that the book doesn't talk about but matter a lot in real time is that you need to sample a lot of samples at once. For example, if you subdivide your pixel into 16 grids, you need to sample all of them at once. So that can be 16 times more expensive for real time. Also, stratified sampling also suffer from curse of dimensionality, but we usually just stratify certain dimensions. For example, we just stratify the initial rays, so stratify the pixels rather than say when we sampling materials, sampling lights, we just don't bother to do stratified sampling again. All right, so the next section talks about importance sampling. Importance sampling is about for a Monte Carlo estimator like this. It converges more quickly if the samples are taken from the distribution that is similar to function fx. Of course, if we already know the perfect distribution, we don't need to estimate it. But if we can have something kind of close, we are able to reduce the variance somehow. So yeah, if we have a using a distribution exactly as the function, just like proportional to the function, then we have a constant. Then we don't even need to do integration. We have variance of 0, but that's impossible to get. But if we have seen something relatively close, and I really like this example. This is more real world kind of example is like we have this Gaussian function which spike at middle 0.5, and for most of the ranges it is 0. It is almost 0. And if we just estimate that with Monte Carlo integration, we get a pretty large variance because most of our samples contribute little. And we need to be really lucky to get a sample in the middle. Yeah, but if we draw from a distribution like this, then we have a high probability to draw samples in this middle area where the sample have much larger contribution.
Yeah, I do like this example because the original problem is if you had the distribution already, we wouldn't need to do any work, but that's a self-referential argument because how do you get it if you are? How do you get something that you're trying to compute? Sorry.
Yeah.
How can you compute something using the result of your computation as the base of your, algebra math? And it's completely not redundant, but cyclical reasoning. Whereas this is more, okay, well, if we know that most of our stuff is going to be coming in this one range, we can only sample in this one range, or mostly only sample in that one range, and not waste a bunch of time sampling all the places where there isn't going to be any contribution, or very, very little contribution.
Yeah, we still need to sample those areas. We can't get them into zero, otherwise we have a biased situation, but we can get their probability to be really, really little. Yeah, of course, if we have some bad distribution to use, for example, like this is the opposite of the above one, basically. And then we have even larger variance than just sampling from a uniform distribution. So yeah, if we sample from this is like 5.4 higher variance than the uniform and 36x higher than the better PDF.
Wait, could you scroll back up to the initial one? Like I noticed that it said like the PDF returned 4.6 between 0.135 and 0.15 and 0.135, but the spike appears between 0.4 and 0.6. Is it saying that like even with an imperfect PDF, as long as actually
The
I'm not
whole
sure.
reason we need this is we don't know the perfect PDF. So anything that closely like kind of close to the shape of the actual function will help. But of course, closer the better.
Okay, I see what it's trying to do. Like even if it's not perfectly overlapping,
Yeah.
even if it's like somewhat matches the shape. Okay.
Wait, is this right? Because it says it's plotted in figure 2.2b, but I feel like that does not match.
You mean this? And
Yeah,
this?
because isn't it so like they look very different. Am I wrong? It's like
Oh
this,
yeah, this is 4.6.
and it goes up to over
This is
8,
like 8 something.
and the range is in the wrong spot too, because it's after 0.4, but the piecewise doesn't even include 0.4.
Yeah, that's what I was confused about. I don't know if it was a typo or whether they were still intentionally choosing a imperfect PDF but had a similar shape.
Oh yeah.
I feel like it's a typo because on the graph it covers the spike, so I feel
Yeah,
like they
it's
wanted to
just
cover it.
the graph is perfectly cover the spike, so I don't even realize that something is wrong at here.
When it says figure 2.2, right underneath the text of the piecewise, sorry. Oh, okay, it's right there. So it's a link. Yeah, I was just making sure that's actually figure 2.2.
Yeah,
Yeah, that is kind of weird.
I feel like that's a typo, but
Yeah, I think we can understand what they're getting at though,
Yeah.
even if those don't match.
yeah, because I guess like it's not actually this wouldn't work. Like this one wouldn't actually work as an imperfect PDF because that's what their next example is when the spike in the PDF doesn't match the spike in the actual function, then the variance is even worse. So
Yeah.
So it can be imperfect, but it can't be like missing the spike. Then it won't work as well.
Yeah, so either this is wrong or the graph is wrong, but yeah, the other possibility of typo is they use different distribution for the graphs. All right. Any questions before we move on to MIS? Yeah, so for MIS, multiple importance sampling, the basic idea is that we have integrals that are product of two more functions, and yeah, each with its own distribution. And it is often possible to derive separate importance. Sorry, what you said?
I think that was just echo.
Okay. Yeah. So it is often possible to derive separate importance sampling strategies for each individual factors, but not as a whole. For example, there are light importance sampling and there are material importance sampling, but how to combine them together. And yeah, if we have, for example, if we have two sample distribution PA and PB that matches the distribution of FA and FB exactly, and then if we use PA as our distribution, then we get an estimator like this, which the variance depends on FB. And if we use PB as distribution, we get variance depend on FA. So still, we just can't get a perfect, well, not perfect, but not even good enough distribution to cover both one. And MIS, the MIS basic idea is to address this issue by draw samples from multiple sampling distributions and then weight them with some heuristics. So yeah, the weighting function choosing such that the expected value of this estimator is the correct integral. And this is just generalize the MIS into more distributions. So a good choice of this weighting function is given by balance heuristic. To be honest, I'm a bit lost at here as well about how this balance heuristic works.
The next equation I think makes it a little bit clearer. You can see it's I guess the sample at that point, the value of the sample divided by the like sum of all of the probabilities you drew that sample for each from each distribution. So like if
Yeah.
so in that next one, like if you drew X, then you do get the what was the probability of drawing X from the first distribution and added to the second one. And you just do that for all of the different samples you take. Because
Yeah, makes sense.
it just has to satisfy those rules they mentioned up above. The like, yeah, when the so yeah, when a sample is not zero, the sum of all the all the weights for that sample equal one. So then it's like, so you're not taking something with higher probability than it's possible.
Yeah.
I like that the last one where they mentioned that the weight of a sample is zero if the probability of drawing that sample is zero. That's cool too because that means you don't need to only use distributions that cover the full range. Like you can use some distributions that focus like only on a specific range and return zero everywhere else. You just have to adjust your weights to make that work.
So yeah, there's this balance heuristic, and power heuristic is just doing balance heuristic with exponent beta. And in PBRT, they have beta hard-coded to be 2, so they just use square root.
You mean square?
Oh, yes, square. Yeah, I was confused about why they use square root for when they have power of 2, but yeah, it's square, not square root. Also, MIS can be applied even without sampling from all the distributions. This is known as single sample model. And yeah, we basically still use the balance heuristic for that. Shortcoming of MIS is that if one of the sampling technique is already very good at matching the integrand, it can increase variance. But for rendering applications, since we draw sampling from various sources, so it will almost always be worthwhile. MIS compensation. I'm also confused about this.
Yeah, it's interesting. I hadn't heard of this before. I think it's basically because like when you have multiple distributions, if you don't actually need them all to cover the whole range. You only need one because then the
Yeah.
weighting makes it work out. So the idea is that if you should adjust your PDFs so that the ones so like where there's like a low frequency range, just make that 0 because you don't want to generate any samples in that area because it's a low probability area anyways.
Yeah, makes sense. As long as we use correct weighting. Yeah, and then Russian roulette is also a technique to just skip samples, which make small distribution. So we often have estimator of a form like this, which is some kind of BRDF and visibility. And BRDF we can evaluate directly, and visibility require we trace another ray. So if we get this, we get 0, then it's not worthwhile to continue to evaluating the visibility. But also we can skip evaluating estimator if fx is already pretty small, but non-zero. But then we introduce a bias into the estimator because we always underestimate. And Russian roulette solves this problem by skipping rays when the fx value is still not 0 yet, but we compensate for it so we can skip them. So we select some termination probability, and this value can be chosen in any manner, and just different sources on how to do Russian roulette have various different idea of how to choose this. At least that's what I read before. And yeah, with this probability, the estimator is not evaluated for a particular sample, and we just use some constant. And yeah, otherwise the estimator is evaluated, but yeah, it's weighted by the factor 1 divided by 1 minus q to compensate that we skipped some sample. And yeah, we have the new estimator like this, which if we calculate its expectation, it's the same, so that's okay. And one thing is that Russian roulette is not a variance reduction technique. It will always increase variance. But it will improve Monte Carlo efficiency anyway. And yeah, if we don't use Russian roulette, we need some like cutout anyway in practice. Like we just cut off after a certain number of bounces. But Russian roulette is a better technique to just let us to skip samples that make smaller distributions. And the final part is splitting, which I also had trouble understand.
I just want to side note comment that your stream quality has gone into the toilet, and it seems to be Discord just compressing the heck out of the text. So we can see where in the chapter you are, but the actual text is almost illegible. So that's annoying, but not something we can do anything about.
Yeah, but yeah, as long as I'm still in China, I guess that's
yeah. Ain't much we can do, but
Yeah, it's not too bad to just follow along separately.
Right. Just want to let you know.
Yeah, I guess so this is just about splitting up the number of samples you take for each dimension, it looks like. So yeah, I guess so when you pick your I sample, which is coming from that X probability, every time I increases, you've done N samples from the Y distribution.
yeah, I guess so. So I'm confused about those math symbols, but in reality, that just probably means, for example, we trace one ray, and then when we scatter, we put multiple samples, stuff like that.
Oh, true, yeah. Yeah, I guess it really is just a nested for loop, isn't it?
Yeah.
And I guess the math just works out if you do the one over. That seems very simple to just divide by the number of samples of each, but I guess it works.
Isn't it kind of like an idea of like averaging the contributions?
I guess so, yeah, because you'd have like 1 over m's multiplied by the number of n. So I guess it just kind of works out that it averages.
All right, I think we are done with this chapter. Stop streaming.